Hi, everyone. Thanks for joining this virtual talk today. I'm Apurva Mehta, and I'm going to be talking about why stream processors need to evolve. So here's the outline of the talk. Basically, there's really three parts to it. We talk about to start with the first two parts are what's hard, or, really two components of why stream processors need to evolve. One component of why they need to evolve is, it's universally accepted that it's really hard to develop streaming apps. So we're going to go in and dig into what I think the reason it's hard to develop those apps. The second part of the talk is, talking about why it's hard to operate streaming apps. And this is also a big complaint, especially once you're stateful stream processing applications. No, everyone finds it super hard to operate. No particular stream processor has a good rep for operating streaming apps, stateful apps at scale. And we'll go into the reasons for that. And finally, we'll put those two things together, talk about what we can do about it, and basically suggest the direction of evolution for the stream processors. Okay. With that, before we dig in, let me just introduce myself a bit more. I've been in the Kafka ecosystem for many years now. I was joined Confluent back in 2016. I did things like Git98, which was to add transactions to Kafka. I was one of the lead engineers on that. I went on to lead the KSQL and Kafka Streams teams at Confluent. And finally, I co-founded Responsive in, in early 2023 to focus on solving some of the problems I talk about in this talk. But it's really Responsive is a platform for Kafka Streams that makes it significantly simpler to operate by separating compute from storage, providing a control plane, and so on. Okay, so let's move on to the first part of our talk, why it's hard to develop streaming apps today. So in the last, several weeks, years, I should say, I've been talking to users of Kafka, and I've kind of split, here's what I found in terms of the major use cases of Kafka, right? And the way you can read this is that the use cases at the bottom of the pyramid are the most common and least sophisticated, and the use cases towards the top of the pyramid are more common, and in some cases more sophisticated. It's not strictly true, it's very hard to categorize, but roughly true. So, don't yell at me if you disagree with some specifics. There's always going to be a counterexample to everything I say about these use cases and this categorization. Okay, so let's go into these use cases one by one. And in general, the point I'm trying to make is that even though there are many different use cases, they'll be served by different tools, but we only have very few stream processors. So the market or the audience expressed preference is different from what we're being marketed to. That's the point I'm trying to make. So let's go into that. So what is a pipe to, what do I mean by pipe to move data? A pipe to move data is what you can think of Kafka as a dumb pipe. So, you're just collecting data from a bunch of sources, doing minimal or no transformations, and dumping it into a lakehouse, warehouse, S3, so on and so forth. The most common use case for Kafka. And also, typically, if you have this kind of use case, you can use something like Bento, or I think now it used to be the name changed, but Bento is common. Kafka Connect is very common. These systems have simple transforms. Bento has some stateful joins, simple joins kind of semantics. But typically, if you're using Kafka as a dump pipe, that's kind of all you need. The second use case category is data integration. So this one is different from being a dump pipe because you're doing a little more sophisticated processing in the stream. So typically this looks like is you're collecting data from multiple source databases and you're kind of either denormalizing it because the source data is highly normalized. Maybe it's a mainframe, maybe it's an old data model from like 40 years ago. And many companies pull the changes off the mainframe, create, join, enrich them to create semantically relevant business objects, put them back in Kafka, and then those events feed online databases, real-time apps, more sophisticated, much more strategic use case of data in Kafka. And what I found surprisingly is that many companies expose this functionality through custom frameworks. So a custom framework is it could be built on a stream processor like Flink or Kafka Streams. It could be built directly on the producer consumer. Many times it's built on the producer consumer directly, but what developers or employees at the company that's doing data integration typically don't use stream processors directly. That's what I found, which is interesting because this is one of the classic use cases of stream processing, but multiple companies, a good majority of companies don't expose the data integration APIs to, they don't, they expose custom APIs for developers to do data integration, which I found interesting. The third category here is a message bus. Kafka is a message bus. So this is like what you call an eventing system. You want async communication between microservices. You could have used a queue for it, RabbitMQ, so and that's kind of also players in the space. You just need to communicate between microservices, and Kafka is just the medium for that. You don't really need durability of the log or any of the fancy features of Kafka, transactionality, or anything like that for this use case. And here the Kafka clients rule, like if you have that use case, you just want to consume a stream of events and do something with it, just use the consumer. If you want to just write some event off your app, just use the producer, and it's fairly straightforward. And finally, the category is real-time apps. Um, this is, I would say, the apex use case for Kafka. This is things like alerting, fraud detection, any kind of limits, ad pacing, so on and so forth, where you're tracking usage, you want to limit usage within a budget, you're doing real time, mostly aggregations, but sometimes joins to kind of compute state in real time and react to it in real time. These are the classic popular use cases of Kafka, um, which you hear about all the time. But um, and I would say it's the best use case of Kafka. It's one of the great use cases. It makes lots of things possible. Kafka and real-time apps that wouldn't have been possible without it at scale. And for real-time apps, Flink Kafka Streams are the stream processors that dominate that use case, which makes sense because they provide stateful stream processing APIs. And people can use them to build very sophisticated and scalable real-time apps. Okay, so those are the use cases. The thing is that even though what we've seen is people have definitely self-selected into using different technologies for different use cases. Yet most stream processors that you see on the market, this is just a subsampling. Will kind of claim to be good for every use case, and they just differentiate on different things like form factor, language, so on and so forth. But in reality, people don't use it. There's definite preferences that developers have expressed, but the marketing then of a typical, this is Flink. I don't, it was easy for me to find, but they claim to do everything, right? And this is very typical in the stream processing world. And I think that because the developers who have the bad experiences pick these heavy stream processors for use cases that they're not suited for, they have to kind of contort themselves into using the stream processor, right? They try and fit the limits or the peculiarities of that stream processor. But and it just feels bad. And that's kind of the root. The point I'm trying to make is this is the root of the bad developer experience. They're using the wrong tool for the wrong job, right? So for example, like take for data integration. Let me just take a moment. And for data integration, developers need really high cardinality joins, right? I've heard cases of 100 or 200 joins in a single app. They don't need fancy windowing. It really doesn't, they like to kind of accumulate, like for example, for denormalization, you just want to accumulate fields in a given record over time. You don't need fancy windowing semantics for that at all. You need one global window and you want to be cutting stuff off that window on a periodic basis. But developers are forced to use windowing for TTL, for example, which just makes a mess of their app for data integration because they don't really need any other thing of windowing. And finally, many of these, people don't care about the schemas for intermediate join results, right? You are doing a massive n-way join into one record, and if it's done pairwise, you actually don't care of any intermediate state. You just want the final state. You have the input states, schemas, I should say, and that's the only two things you care about. Yet, most stream processors explode state. They maintain pairwise state to do joins. So if you have 200 joins, you have hundreds and hundreds of state stores. It explodes states, makes it hard to operate. Again, as I mentioned, to get TTL features, if you want to clean up state, you have to use Windows or write apps out of band, which then makes either the app harder to reason about because you're using features you don't need, or you have to add an app to do a cleanup. It's just painful. And especially for the ones where you're doing pairwise joins, you have to do pairwise schema declarations, complete overhead for the use case. And if you get into dozens or hundreds, especially joins, this is really, really hard from a developer experience perspective. It's hard to write the app, it's hard to evolve the app. It's hard for anyone else to understand why you've written an app this way. And that's where it starts getting a bad rap. These apps are impossible to develop, and especially as a team, and especially to maintain over time. I think that's where the reputation comes from for stream processors when you use them for the wrong purpose. Yeah, so that's kind of what I'll end this section just repeating that message. Like when you try and force a square peg into a round hole, it's painful, it doesn't work. Sometimes you may squeeze it, but you're never going to be happy with it. And that's kind of what the developer experience for stream processing use cases look like for most people. And I'm talking about the cases where you use existing stream processor for data integration, or for message bus, right? It's just the wrong tool for that job, and then it just feels like forcing a square peg in the round hole, and that's where the majority of the dissatisfaction comes from. And I should add, if you use a stream processor for real-time apps, people are typically happy with the developer experience of doing that. It makes sense to use it for that purpose. So when you use the right tool for the right job, you don't feel like this, right? But the four use cases, broadly speaking, and if you use stream processors for any three of them, you're going to feel like this. That's the point of what I'm trying to say. And finally, I just talked about the developer experience, right? Of building the apps. I have not talked about testing, integration with the CI/CD environment, debugging. Those are also problems with Kafka applications, whether you use a stream processor or not. And this compounds what I just said. So you use a stream processor for the wrong use case, it feels very awkward to write the app, evolve the app, maintain the app. And then you have these problems testing, CI/CD integration, debugging too. And that's where it gets really painful for developers. Great. So I'm going to switch now to talking about why it's hard to operate streaming apps today. So this is the second part of my talk. And the big point I'm trying to make is that the traditional stream processors, Flink, Kafka Streams, are still generation one, right? And they've not evolved to meet today's cloud environments and expectations of the cloud. And that's kind of the root cause. So let me tell that story. So Apache Flink was created in 2014, Kafka Streams in 2016, and this by and large predates a couple of big trends in the industry. First, around 2016, 2017, Kubernetes really started going mainstream, right? This was post Kafka Streams and Apache Flink, right? Finally, storage options started exploding. I would say the trend, specifically Snowflake, Redshift, but like object storage as the medium specifically for data systems as the durability layer started becoming a popular idea with those big analytical databases. But this was also after. Now, the dates are fuzzy here, but this is also by and large after Kafka Streams and Flink were designed, right? So basically, today's data systems, modern versions of databases, modern data systems kind of, you know, definitely take object storage as the default storage option, but also fit much better with Kubernetes. Neither of which statements are really true for Flink and Kafka Streams. Not like you can't use Flink and Kafka Streams with Kubernetes, but really, they're not Kubernetes native, like a controller operator model. Um, so that's kind of what my hypothesis is here, that they predated these big trends, and we feel that when we operate apps built with Kafka Streams, KCP, and Flink. Yeah, so that's the point I just made. Because we're designing a pre-cloud and pre-Kubernetes world, we get a pre-cloud and pre-Kubernetes operational experience. And what does that actually look like in practice? So let me just cover the symptoms of what operational pain with running these stream processing apps built with Flink or Kafka Streams looks like. One is reliability. So these examples rebalance restores performance specifically to Kafka Streams, but really reliability affects Flink apps too, right? Because they, for example, both in Kafka Streams and Flink, your persistent state is either in Kafka or S3, but in Flink, the whole job has to stop if you lose a node until the state is rebootstrapped. If that's a lot of state, it could take a long time. The whole thing is shut down. That's an availability issue for Flink, for example. In Kafka Streams, that's a state restoration from Kafka. Same thing, less bad was just one partition, a few partitions pause, but it's still an outage for those partitions. Kafka Streams has rebalancing that could bring multiple partitions down. Anyway, so the rebalancing, for example, is a clustering load management control plane function built into Kafka Streams, again, pre-Kubernetes. So these are all the examples of reliability issues due to control plane or data plane's design being pre-cloud, pre-object storage. Finally, flexibility. This one is easier to grok if you have coupled compute and storage. For example, elasticity is impossible, especially when you have large amounts of state. We know that from decades of examples. Deploying these apps frequently results in reliability issues because there's downtime during upgrades. They're not really something, I've heard people say that we throw salt over our shoulder before we deploy these apps because typically something breaks, but you need to do it. So if you know something is breaking when you do a deploy, you just do fewer deploys, you lose flexibility. And finally, toil, like both Kafka Streams and Flink have millions of configs, almost, this is like an n-dimensional problem because changing one config affects other configs, and finding the right set of configs to make an app stable or performant is really a highly iterative process, takes high degree of expertise, and that process is just a lot of toil because you're going to have reliability issues until you find the right configs. And if your scale changes, you get more traffic, more state, more key cardinality. These configs typically have reconfiguration has to keep happening, resizing needs to keep happening, which is a hell of a lot of toil for developers running these systems. So those are the symptoms of problems with Gen 1 architectures for stream processing, like stream processors like Kafka Streams and Flink. And I wanted to take those insights to suggest what we can do about them as an industry. So the first thing is kind of the obvious. To make it easier to operate, you just need to modernize existing stream processors. For example, Kafka Streams has, um, you know, embedded RocksDB, that's embedded state. It has embedded task management, which is load distribution, liveness detection. That's kind of control plane functions. It's embedded in Kafka Streams. Again, pre-object store, pre-Kubernetes. That design made sense, but it causes all the problems I just talked about. So the obvious solution is, is to unbundle the state and control plane layers of Kafka Streams, right? And it would look something like this. Like Responsive has built slateDB for this purpose, which allows you to use S3 as a backend, durability layer for streaming state storage. Very fast, low latency range and key lookups, high write volumes, but persistence and replication on S3 is what slateDB allows, solves significant class of state management issues with Kafka Streams. And then, moving task assignment and rebalance execution out of Kafka Streams significantly makes it much easier to administer these clusters of Kafka Streams apps. That's Kubernetes native. So the control plane is remote and centrally administered and automatic, and it executes policy through an operator via Kubernetes, much more aligned with what developers expect from other services running on Kubernetes. So in this world, Kafka Streams is like any other Kubernetes apps, administered like any other Kubernetes apps, significantly more aligned with operational expectations of developers, which solves, I would say, the first problem of operations of these apps, especially when they're stateful at scale. Okay, the second suggestion I have is a little more complicated, I would say a little more novel. And the suggestion here is to, instead of what we saw, the pyramid, right? Kafka Streams Flink is great for real-time apps and really not been successfully deployed for the other use cases, right? So instead of forcing these systems for all use cases and creating developer pain, pursue a Lego approach, right? And the analogy here is if all you have is a hammer, everything looks like a nail, and that's kind of how we use current stream processors, right? You're trying to force them into every use case, and it's just not a fit. It doesn't get the job done, or if it does, it's a significant amount of effort and just feels wrong, right? And the alternative is, don't give people hammers, give them maybe some simpler abstractions, simpler building blocks to build. If it's a hammer they need, well, they can construct that easily for themselves. If it's a screwdriver they need, they can construct them for themselves. So it's much less a full monolithic system that is inflexible to a more modular system that gives developers the flexibility to do the job at hand. So for example, right, I'm taking Kafka Streams. This is what roughly your Kafka Streams deployment, a single instance looks like. You have a code at the top, and then you have a core set of, core data flow runtime that has operators, that exposes an API, that schedules tasks locally for execution based on your logic. And then you have subsystems that do state management, cluster management, manage IO, so on and so forth. So this was fully vertically integrated behind a single API, all of the systems. And the alternative is to kind of break that up, right? Provide each of those layers separately with clean interfaces in between so that developers can put them together in a way that makes sense for the use case at hand. So, that that basically starts with the building blocks. We kind of already have done that for Kafka Streams, where we provide state storage, provide control plane um, outside Kafka Streams itself. And then the idea would be to kind of create a general purpose runtime, maybe in a language like Rust, that that implements data flow and implements some operators really, really well. Then layer on, but decouple that from the API exposed. Then layer on that different API frameworks. Like maybe you can use, if you want to connect different systems, you can use the same runtime. Maybe you don't need the state store, but you need the control plane, right? So you can have like a line through here for connectors. SQL functions would maybe use the whole thing. Stateful functions the whole thing. You can even provide the existing Kafka Streams or Flink APIs on this runtime. And so there's the API frameworks, and then finally, native language bindings. This is also something stream processors. I didn't mention it, but most stream processors strongly prefer Java, which is also a bad developer experience for people who don't quite know Java but need to use them, right? So provide different language bindings as a first class construct. And this can be designed, right? I think we have new technologies that allow this native experiences in multiple languages on the same stack. So that would be like the Lego blocks, like really, 4 layers of Lego blocks. But if you take that approach, it should resolve almost all the major problems people have with stream processors today. Okay, obviously that's easier said than done. And these are just the open questions I have. Like, first of all, is that, maybe it logically makes sense. What is the practical solution to those, a general purpose runtime? What language you write it in? Is it practical from that language to provide native bindings? What is the features of the runtime to enable different API frameworks, right? Those are open questions. And that leads to what frameworks should we support? Like, can we have different frameworks for those 4 use cases? Or do we need more frameworks? Open question. And finally, you're not going to write it for all languages. What do people actually want to build streaming apps with? I would go TypeScript, Python, and Java, I think, should be the leading ones, but we should just be clear about that list and then also build that it's easy to extend when new languages eventually come online and become mainstream so that this extends to that. That's it for my talk. You can find me on Twitter or LinkedIn. That's my information. And yeah, I really appreciate you taking the time to listen to this. Thank you.
Oh, hello. Hi. Hi. Thanks so much for the wonderful presentation.
Oh, yeah.
Yeah.
No
Okay,
problem.
great.
Thank you.
Awesome. Okay, cool. So we can take questions from the audience live here, and it seems that we do have one right now. So I can just read this question loud, and then you can address. Would that work?
Sounds good.
Okay, perfect. Okay, so what is your operational view for running stream processor at a platform managed by a platform team, such as Flink, versus running it at the user side managed by a user team? What is the troubleshooting experience consideration behind that?
Um, so, so I guess the question was, what's the difference in the operational experiences in the two models, platform team versus application team?
That's how I interpret it.
Yeah.
Yeah.
Yeah, I think I think without more context, it's hard to understand exactly what they're asking. But basically, um, I think the considerations between the two models is really the way I see it is that, when the stream processing app is kind of in the critical path, right? So if it powers a product that needs to be online all the time, typically, unless it's like the massive companies like Netflix or, those kinds, typically companies just prefer the application model. So the team, it's like your web app, it's like any online application. Completely. owned and operated by one team is the preferred model because it's much simpler. Um, and the ownership, I think the main thing is ownership. It's clear who carries the pager and it's clear whose responsibility and outage is.
Yeah.
And that's very important for online applications. Then when it's more when the applications are less in the critical path, and also especially what I've seen a lot for especially Flink and Flink SQL, a platform team will manage Flink and allow you to run Flink jobs, but the audience for those jobs are more data engineers. They're more like offline-ish, or at least nearline use cases. Like if there was a problem, it's not going to bring down the product, right?
Yeah.
And this could be like in some gaming companies or like in some crypto companies to analyze data quality to alert on data anomalies, those kinds of things. Um, Flink and the central model is used. But that's the main difference, whether it's really, really in the critical path or not, that's where companies choose one or the other, from what I've seen.
Got it. Got it. Okay, great. And we just got another question coming in. It could be part of the follow-up, but let me read it and then you can see how you would like to answer it. Okay, so here goes. How do you think about stream processors and agents? Will next-gen processors become more agentic?
Yeah, I think that's a very good question. I mean, in theory, you'd expect agents to be basically stream processors. They need real-time data feeds, they need to react to them, they need to make a ton of decisions in real time.
Yep.
And the lower latency, the better. So more than, like the event-driven model makes a lot of sense for agents. And you also see it, a lot of the modern architectures, in some sense have some element of being event driven, although none of them I think actually use Flink or any Kafka streams or any modern stream processors to deploy agents. But I think I think most likely, there will be a stream processor that backs the most popular agents. And I also don't think it'll be either Flink or Kafka streams. It's most likely going to be something new because, AI is moving so fast, and both Flink and Kafka streams are over 10 years old and roughly been the same for 10 years. It's hard to imagine just on that alone that they're going to support millions of, like just think at scale agents. If OpenAI has agents they have like 1 billion users a month, what you're going to have billion, like how is that going to be modeled in Flink or Kafka? It's impossible, right? So I think, some much more multi-tenant first stream processor will need to arise to power that at scale. I think for toys, like a lot of vendors will do, oh, you can do agents in Flink, and yes, that's a great demo. But I don't know how it's going to scale practically.
Mm.
Given all of these systems were built and designed 10 plus years ago.
Interesting. Okay, I'm intrigued. I'm actually going to jump in and ask a question. So, based on your experience and then what you've seen, so how long do you think we gonna get there? Like how long to get to where we can have a processing platform that can power the scale of AI? And what are the technology that you're envisioning? If it's not Flink or Kafka, would that be a
I mean,
variation of both?
I'm
Yeah.
pretty sure that these companies, like the big scale AI companies, already have their own frameworks already, right? It's just a question of time whether they make it open source or not. I mean, just think about it, right? Like if you have at OpenAI scale, like their O1 Pro or whatever already is an agent, right? Now, assuming there are hundreds of millions, how is that going to be modeled in Flink? Like, just how is it, like, literally, how are you going to do it? Right? There's so much overhead per job, so much metadata per job, state storage, there's no isolation between jobs in a single cluster. Or are you going to have one cluster per agent? Think about the overhead of that when you have like 100 million plus agents. Just think about it. You know?
Yeah, yeah. Well, check out
So
our Ursa. Yeah, maybe Ursa can do that.
maybe I actually not checked out what Stream Native is doing. It's just hard to imagine.
Yeah,
like I'm just saying, it's like a 2 or 3 orders of magnitude more
yeah,
in
yeah,
scale,
yeah. And
right?
it's changing rapidly
And
so fast. Yeah,
yeah, and no, but agents basically like if you have an agent or multiple agents for every person on Earth, and that's the vision of these scale companies, where
yeah,
you're gonna have like 20 billion jobs. What you know?
yeah, yeah,
I
yeah,
just don't think it's
yeah.
you
My
need
brain's too small
something.
for that. Yeah.
Yeah.
Cool, awesome, thank you. All right, we're gonna take the last question given the time we have. How do you handle monitoring experiences for Kafka stream processors for the platform team if the processors are running at client side? It's a very operational question.
Yeah, that's a good question. I think generally observability for all streaming is difficult, right? Like, um, so like typically in because I asked about application side stream processors, right? So far, the state of the art is you basically deploy your own Grafana and your own observability stack for your application. A lot of companies kind of templatize all that, so you get dashboards by default for every app. I think generally what's missing is like a by default data flow view, right? If you have many apps in, reading and writing from each other's inputs and outputs, um, when something breaks, finding out where that is, I think is a gap, right? And I think that is where maybe you probably need a platform team, some central entity to kind of help give you that view, which for the application side is a missing piece, I think. I mean, for sure. Unless one team owns all the apps, right? Then they can kind of figure this out. But if many teams own different parts of a big pipeline in the company, it's a very
Yeah.
difficult observability problem that for application side, like Kafka Stream, the client side stream processing is not solved, I would say today. Much easier. That central view is much easier with a central model like Flink, right? Because you at least I don't know if Flink actually does it well, but at least in theory can do it well. But that's how I see it.
Awesome. Alrighty. Okay, we're at time, and I want to thank you for joining us and spending time with us today, Apravat. It's very insightful, and thanks again for having all of us listening to your wonderful talk. And for the audience, if you need to connect or reach out to Apravat, please feel free to do so in the network session on the homepage. Alrighty, that wraps
Okay.
this session up, and I'll see you guys in the future sessions.
Thank you, everyone.
Thank
Bye.
you. Bye.